Hello everyone, it's Marco speaking from Riverlane. Today I just like to show you Deltaflow, that is our product. We've been working in the last 6 months with the target of developing a better control stack and an operating system for quantum computers. I'll alternate a few share screen, so I'll try to be as smooth as possible, but as everyone knows, Zoom is not as a live presentation. So let me just start with defining the target, or at least describing our goals for Deltaflow. So we want you to be able to accelerate your R&D, and that's because we think that if you work with FPGAs, and I will explain what they are and why they are needed, there is a lot of complexity that we can help you with, and that's one important goal of Deltaflow. The second important goal is that we believe that a full stack visibility and a full stack control of your system is important to leverage all the possible aspects of your quantum hardware and give you the extra oomph that you need to achieve your goals. The last point is low latency, and we believe that low latency is important because there are applications there are a special class of quantum algorithms that will significantly benefit from having low latency and having a way to improve your time to control of the hardware. And we are working, Riverlane is working with in a collaboration with all the biggest UK startups in quantum world and MPL and ARM. And this is because we believe that what we can achieve is an hardware abstraction layer that I will present in a second, that is important for enabling developers, different developers, to write code and test it on different platforms and get the best out of all the possible implementation and possible hardware solutions. What we think is relies on latency or low latency. We have a list of kind of a wish list, if you want, of all the future applications and current applications that could leverage faster control loops, and they are randomized batching, VQE, QAOA, and many more. And to do that, we need the application developer to be able to address the hardware, and at least to address the control hardware. What I mean with control hardware is that in a traditional or in all the quantum computers that we have seen so far, we have this model, this stack that defines this hardware stack that defines your control stack. So you have a heterogeneous system with one or more CPUs. Then you have one or two layers of FPGAs that are devices that you can reconfigure quickly, and they have extremely low cost compared to designing your own ASIC, your chip. But they still provide you with the capability of designing the hardware the way you want it. And this is important for timing reasons in controlling digital and analog components like lasers, AWGs, and so on and so forth. The important layer is obviously the quantum layer. And what we think that is represented in this stack by the blue and green blocks. What is important to in this slide is that we are working in defining an hardware abstraction layer, and this slide can be read as you want. This hardware abstraction layer can be moved up and down in the stack. We are still tuning with our partnership where best to put the hardware abstraction layer, but still the idea behind is that it should give you all the performances that you need. And it should let you use different type of quantum machines around the same, ideally the same algorithm with no changes. The other important bit that I want to present today is the way that we think the Deltaflow can accelerate R&D, and this is based more on a shift of paradigm that Deltaflow enables. Deltaflow matches the data flow model of computation, and this is kind of becomes important when you want to target a distributed system. I have an example here on the top part of the slide of a traditional control stack with a CPU, and normally you will have a kind of large node here that is an FPGA, and this FPGA will control different hardware that are driving the qubits, different hardware as in lasers or again AWGs or other digital components. Now the problem of this solution is that when you need to control more qubits, what's likely going to happen is that you will need more nodes, and the complexity of this central node will grow. And this complexity will reach the limit of the existing technology, making it costly, difficult to maintain, and expensive in terms of time and bug discovery, etc. Deltaflow instead enables us and every developer to use a more distributed approach. So we have the concept of nodes, and nodes are connected in a graph, and you can have any topology you like. You can have open topologies, connected topologies, cyclical topologies, and that lets you target that lets you tailor your with your code the existing hardware that is creating your quantum machine. The important bit on that is that because we are splitting the complexity of that central node across multiple nodes, we are moving towards a simpler and modular approach, and modular approaches tends to be easier to test and to verify. So our goal is to define blocks that can be used to create larger systems, and they will, as a side effect, it's a nice one, they will reduce the total cost of the solution by using cheaper hardware. Now, if I think the second important message that I want to deliver today is that Deltaflow is not just an idea; is a product that we are currently in beta testing. I want to show you today an example of Deltaflow integrated with an existing control stack that is called ARTIQ. There is a link at the bottom of this page if you want to know more about ARTIQ. And I want to show you, I will stay for another probably 5 minutes on this set of slides, and then I'll show you a bit of code and interactive. There will be a bit of interaction in a terminal. What I'm going to show you today is, first of all, is a demo, and is a demo that is still increasing in terms of what we want to do and what we want to show. But on its basis, it contains an ARTIQ emulator. So we have a way to behave and show the behavior of an ARTIQ system, or part of it. And the second part that we have done, and I'm going to show you, is we have coded with Deltaflow a simple example, a simple program that is a Rabi oscillation. And this is because we code it in a way that should show you the benefit and idea behind local feedback, and having the advantages that you can gain by having low latency. What was the kind of the nice to have that actually happened was that by doing this demo, we can show you that we can integrate Deltaflow to existing control systems. We don't force anyone to throw away the existing control stack, but we have ways to integrate to existing ones. The second bit I want to show is that with this kind of Lego brick approach, we can ease the pain towards programming an FPGA, and we can use a more software-oriented approach for designing, testing, and verifying. And as I was saying, the last bit is that because we can connect to this existing system, you don't have to replace your current runtime and throw away all the code that has been working fine for you in the last years. A few definitions that hopefully will help. So I was saying the hardware abstraction layer is a concept that allows the application developers to write code that can be executed on all the hardware providers that implement the hardware abstraction layer, and is a contract. You can see it as an API, a contract. And the idea behind is that we want you to be able to write code everywhere without losing on performances, because it's important that you are by generalizing, you don't like lose the edge, and we don't make the quantum solutions less appealing. The second part of second definition that will kind of be I will repeat a lot during the presentation is the concept of emulation simulation. So what we mean with that in a generic fashion is that we want the user to be able to see what's happening inside all the hardware that is involved in the quantum control stack. We are not focusing at the moment too much on the quantum side itself, but we want to show the impact and what's happening in the control stack itself. So there will be mainly CPUs and FPGAs at the moment, but that can grow to cover other types of computational units. Obviously, the other advantage of an emulator is that the emulator is supposed to run on your laptop or on the cloud, and it doesn't need a quantum machine sitting next to it. So it's the way for you to share your system with multiple developers and get like everyone to work at the same time, even if you have a single quantum machine or if you don't have any quantum machine available. The idea, everything in this demo will rotate around this Rabi oscillation, and the Rabi oscillation can be depicted by this graph. It comprises 4 nodes, so the circles are nodes, and what it does is basically sending a sequence of commands that are respecting the abstraction layer specifications here, if you see my pointer, so from commander to emulator. And these commands are always the same in a way. They are preparation, rotation, and measurement. But because we want to show you some the low-level control capabilities of Deltaflow, we can change the angle in the rotation. So the rotate X, as the name says, is a rotation across the X-axis. And we have a variable angle that is generated by this aggregator node. This aggregator node takes a measurement from the system and is using that information of 0 and 1 to actually change the angle and create a low-level control, an example of low-level control. We have a printer node that is for debugging, that is normally something that you won't have on FPGA, and is in this environment instead it lets you see and gives you visibility in an easier fashion via print statements. The important bit here is that this graph is composed of 2 types of nodes. The dark green ones are pure Python nodes, so they're written in Deltaflow Python. And then there are Python for FPGA nodes that are written in MyGen. And MyGen is a language developed by ARTIQ that sits on top of Python, but it can describe hardware, as in FPGAs mainly. And it can convert this description and internal representation into one of the most used FPGA languages, that is Verilog. So this graph is an heterogeneous graph in nature, and the way it's represented in code is actually homogeneous in a way that, because we are relying on Python everywhere, you will write Python and MyGen, but at the top level they will integrate seamlessly, as in this example. You don't really notice which one. There is no special syntax to define to call and connect a MyGen node versus an FPGA node versus a Python node. Now, as I was saying at the beginning, we want to give the users building blocks and building blocks that they can trust. So to do that, what we really care about verification and testing of what we do and what you can do. And to do that, we came up with this idea of multiple steps of verification and testing. And we can see 3 steps, and I will show you kind of a 4th one. So what you have is you can run your graph in a pure Python way, and that will be what we call a Deltagraph run, and that's using Mygen and Python to run the simulation. All the nodes exchange communication and messages through asynchronous channels, and that kind of frees you from all the latency implications. By running in this mode, you can start finding lots of the problems that you can introduce in your code and debug early and catch all the problems early. The next phase is when you are happy and confident with this result, we have a way to move to System C. That is a language that is normally used by semiconductor companies and modeling companies and simulation companies for represent hardware. So by converting your Deltagraph into this representation, you can verify that the hardware is behaving in a way that is as expected. When obviously you can still find bugs here, but when you're happy, final step is you can generate configuration for FPGA and for FPGA for CPU and run it on your system. Just a quick view of what's inside the emulator itself. So the emulator is a model of a set of models actually of the components of the ARTIQ system. And for the sake of this presentation, it contains 1 or 2 CPUs, depending on which flavor you run it, models for memories and no quantum units. And what's inside this ARTIQ simulator is basically the quantum path, the path of the control that is driving the quantum digital analog components. And we have this hardware abstraction layer bridge that is used for connecting all the Deltaflow graph that you can think of and everything that is supporting the hardware abstraction layer specifications. Now, what you get by running it is, running the emulator is different analysis tools as well, and lots of them are high level, so they like tracing of internal transactions like read and write operations, and there are low level visibility of what's happening inside the FPGA itself. That is really instrumental when you are trying to debug like problems with your code or with existing solution. Now I'll just switch to the way we disclose this knowledge, and what we came up with was best way is to give you a story that is the Rabi oscillation and describe it via Jupyter Notebook. So this Jupyter Notebook that is going to be publicly released when we potentially mid-end November when we go for a public release, will contain, and it contains all the building blocks of the graph and everything that is needed for implementing the Rabi oscillation. The nice thing is that it connects to Project Q as a backend, so it does run a realistic representation of the control stack together with the Rabi demo. And if you scroll down all the system, what it does when you run it, it's generating the results that you will read out from a real system of the Rabi oscillation. Now we have different ways to share this information. So we have, as I was saying, this is your entry-level testing view. Then we are providing a way to run. I'm not going to run it here because it takes 1 minute, but we have the same way to run it through a terminal. This is because it's much easier to, as you will see all the logins in this way. We have a way to run the System C conversion. So this run is still using Project Q as a backend, but it has converted all the nodes in System C, and this means that they are behaving in a more hardware hardware-friendly way than the pure managed ones. And then the last thing that we can run with this demo is the emulator itself. So this screenshot, this shell is showing you a boot sequence of an ARTIQ system. And what's the interesting part is because we have our Deltaflow graph connected and we have our hardware abstraction layer in place, you're going to see that after booting and doing all the initialization, we will get some messages with Riverlane Rabi demo. And these messages are request of file commands coming from the Deltagraph that we connected. And the left-hand side is showing the time, realistic time that these transactions will happen on the real system. So this gives you the capability to really understand how a small change in your code can have a large impact on the final result of the latency of your system. So you see we are receiving all these numbers represent internal codes that matches with the hardware abstraction layer specifications. With this, I'd like to thanks everyone. Stay safe, and if you have questions, please do ask Robin and Alex. They know everything as well. Thank you very much. Bye.